So now let's talk about first the different concepts that we have talked about in class, and then then in the end I'll get to just some example of some problems that you might face on the midterm. So the first is this, that if you take a subset of Rn to say that A is bounded from above, this just means that there exists M such that for all A in A here is less or equal to M. So this is what it means to be bounded from above from a subset, right? And now the least upper bound. This is a number, so M here is a least, so M is a least upper bound. If M is an upper bound, and any other upper bound let's call it M bar is bigger or equal to M. Right? So this is what it means to be a least upper bound. And so the least upper bound, so the least upper bound is, this is what we denote by super beta. This here is the least upper bound. Okay, and similarly for lower bound and it, right? And the real numbers have this property that if a set is bounded from above, then it has then there is a least upper bound, right? And likewise for a set that is bounded from below. Okay, so that was soup. And we'll get to this with lim sup and lim f. I'll just review that a little bit later also. But that's another one thing. A sequence. So another key concept in this class is sequence. And let's begin with a sequence of real numbers. So this is a map from the positive integers into R. And again, we denote, so the image, so if you're looking at the image of some n, we typically denote this by an or by an or xn or something like that, where we use the subscript, but it's just the image under this map. So that's a sequence. So for each positive integer, you get a real number. Then for a sequence, one of the first things you were interested in is convergence. So if this here is a sequence, that xn converges to some x here, this here just means that for all epsilon greater than 0, there exists. I've used this symbol, I haven't used it until now, but it's just so hard not to use it. This here means that they exist. It's not on the midterm. but it's a totally standard symbol. So they exist capital N such that if little n is bigger or equal to capital N, then xn minus x is smaller than x1. Right, so this is what it means for a sequence to convert to x, sequence xn to convert to x, and you write like this, or you can write xn and then the limit here as n goes to infinity is equal to x. Both of these are standard to use. So, and then also if a sequence is not converted, then we say it is divergent. So sequence is either converted or it's divergent. And then you have there's this property, useful property. So a lemma, if xn is convergent, then the set, this as a set, this here is a bounded set. Okay, so we talk about that. And then another thing about sequences is that the algebraic properties of sequences. And what are the algebraic properties? They are that if you take two sequences, an and bn, and let's say that an converts to a and bn converts to b, then the algebraic and c is just a constant. Then you have that, so, and often when you combine what I did, there's 1 and 2 before, you combine, you're looking at an plus c times bn, this here converts to a and c times b. This is the first, and this, when I state it like this, it actually combines two of the one properties that we talked about earlier. The second one is that an times bn will convert to a times b. Third property is that if these here are not equal to 0, and the limit here is not equal to 0, then 1 over an converts to 1 over a. And so, of course, this last one, you know, this one implies in particular, of course, that also bn over an converts to b over a. This is just because this property here combined with property 2 that will give you this. Okay, so that's the algebraic properties of limit. Then you have the concept of a subsequence. So a subsequence. So we are imagining that we have a sequence, and often we don't go all the way back like this, but a sequence again is a map from the positive integer into R, and we denote the image of n, like typically like xn. Then a subsequence of this sequence, and this is typically denoted something like this, where you have a further subscript. And this is important again, that this is like equal to f of g of k, where g here, and this is the really important property, that g is a map from the positive integers into the positive integers. And the really important is that g here is strictly increasing. And so strictly increasing guarantee you that these numbers here is taken in the same order as in the original sequence, but you may skip a bunch, right? I mean, you take one and then you may skip a bunch, and then you take another one and then you may skip more, but it's in the same order. And that's what strictly increasing is guaranteeing. And then you have this property that, so you have the theorem that a sequence xn is convergent if and only if all subsequences are convergent. And one of the two directions for this theorem was trivial, because if you have if you take a sequence, then it is, if you're thinking about this map here, G as being the identity, that will give you a subsequence, but that really is the original sequence, right? So the original sequence is a subsequence of itself. So if all subsequences are convergent, well, then in particular the sequence itself is convergent. So one of those two directions was trivial. Okay, now then we had these two theorems, and they were by then. So the thing in mathematics is that things built on each other, right? And hopefully, like each step is fairly trivial, but you build step by step, and then you end up with something highly non-trivial, right? So this here was pretty trivial, but then we used it later on to prove something non-trivial. So this was this monotone convergence theorem. And it has there was two versions of this. You had a sequence xn, and xn was increasing. So that means that the next element is bigger or equal to the previous element. If this here was the case, then xn is convergent. If and only if xn is bounded. If the sequence is bounded. And the sup of the xn, this here is the limit. This here is the limit. And the second version of this is if you have a monotone, so instead of being increasing, it's now decreasing. So the next element is smaller or equal to the previous element. And then similarly, the sequence xn is convergent if and only if xn is bounded from below. And in this case, and if it is bounded from below, then the limit here is of xn is the if. Okay, so that was the monotone convergence there. And it has these two versions, the increasing version and the decreasing version. Then, another important concept was that of the Cauchy sequence. And the reason why Cauchy sequence is useful even for the real numbers, right? I mean, later on we generalized these concepts. There was obvious generalization of the concept of convergence, but also of that of being a Cauchy sequence to metric spaces. But even for the real numbers, Cauchy sequence, you might be interested in whether a sequence is convergent, but sometimes it's much easier to prove that it's a Cauchy sequence than to prove that it actually is convergent. And so if you don't really care about what the limit is, then it's often easier to prove that it's a Cauchy sequence. So Cauchy sequence. So you have a sequence, again, we're still in the real numbers, and this is a Cauchy sequence. It just means that for all, and now I will use also this here. This symbol just means for all, and that's also a standard symbol. It's an inverted A. For all epsilon greater than 0, there exist, again this here, the inverted E means there exist delta, there exist capital N, such that if little n and little m are bigger than capital N, then those two elements are bunched epsilon close together. This is what it means for a sequence to be Cauchy sequence, that the tail of the sequence lies very, very close together. Then let me skip. In my notes I have something about contracting that, but actually there won't be anything about contracting that, so I'll skip that. Let me now next talk about the Cauchy convergence theorem and the Bolzano bias factor. So Cauchy also, let me just remind you that, again, on the midterm, so there are these 5 main problems, then there's a 6 bonus problems. But make sure that you, it doesn't matter which one you do. So you might as well start like with the ones that seems easiest to you. And you can see anyway, it says exactly how many points each of them give. So you can, if you don't have enough time to finish all of it, you can make sure to try to optimize. Okay, so what is the Cauchy convergence theorem? So again, we are in and so the Cauchy convergence theorem is the theorem. Let's say that if Xn is a Cauchy sequence, then Xn is convergent. That's the Cauchy convergence. The Bolzano bias theorem and this Cauchy convergence theorem, we talked about that. So like the concepts, when we in a minute review metric spaces, then convergence sequence that makes sense in a metric space, Cauchy sequence makes sense in a metric space. But it's not, and the statement of this theorem makes sense in a metric space. But it's not always that it holds. It holds in R, but it doesn't hold in a general metric space. The Bolzano bias theorem, statement of that also makes sense in a general metric space, but it doesn't hold in a general metric space. So these are things about the real numbers. I mean, they extend to more than a real number, but you have to, for other spaces, you have to kind of prove it individually, right? So Bolzano-Weier's theorem says that if xn is a bounded sequence, then xn has a convergent subsequence. Okay, so that's a Bolzano-Weier's theorem. The next thing I want to review is what it means for a function to be continuous. So continuity is another important property. It's closely tied together with this sequence, and we'll get to that in just a minute. So if you have So if you have a function, let's say on R, but it could be defined on a subset of R. So if you have a function like this, then we say that f here is continuous at x0 if for all it's continuous at x0 if for all epsilon greater than 0 there exists delta greater than 0 such that if x minus x0 is smaller than delta, then the images is smaller than epsilon. So that's what it means for a function to be continuous. And there was this this theorem or lemma that tied things together. So lemma, if f is continuous at x0 and xn converges to x0, then the images, so the images of this sequence, so that's another sequence, converge to f of x0. So we prove this even in a metric space, but normally we're still in R. Okay, and so right, and then we had the algebraic properties of functions, and they were very similar to this. So let me just review them. So algebraic properties of continuous function. Continuous functions. So imagine that you have f and g are continuous functions. So everything is defined on R. C here is a constant. Well then, property 1 that corresponds to that property 1 here is that this function plus c times this function here, this here is also continuous. And then 2 is that if this function here is never equal to 0, then 1 over this function here is also continuous. And then, sorry, that was not the, sorry, I should not make that the second, I should make that the third property, sorry, that f times t is also continuous. and then the third property would be that if f is not equal to 0, that would kind of correspond to it. Then this function here is also continuous. Okay, and again, I divided it up. When I did it, I divided it up into 4 steps because I separated this out as 2 steps. Okay, and so from this one, we got that, right, just because then we proved that the constant function was continuous, and the linear function, the function f of x equal to x, is continuous. Once we had that, then we just use 1 and 2 here to prove that all polynomials is continuous. And then if we bring in 3, then we have this with all rational functions are continuous, except of course where the denominator vanishes, right? Okay, so that was how you sort of built continuous functions from non-continuous functions. Then we proved the extreme value and the intermediate value theorem. So we had these 2 theorems, and they were proved. So one way to prove it that we did last time was to use this lemma that tied together continuity and sequences. And so we had the extreme values theorem. And this just say that if you have a function, but now it's crucial that this here is a bounded interval and the endpoints are included in this. So if you have a function like this, and this function is continuous, then the sup and the inf over the set here is achieved. So the max, or if you will, the max of f and min of f are achieved. In particular, the function is bounded. So I'll just state it like this, a little bit brief like that. So that was the extreme value theorem. The intermediate value theorem, it said that if you have a function, imagine that it's starting off here and it ending there. So this is like the function. The intermediate value theorem say that everything in between these two is also the image of something. Right? So if let's say that f of a is smaller than f of b, then and y here is between f of a and f of b, then there exists the x between a and b, so that f of x is equal to 1. Again, the functions we're talking about are continuous, right? And they're defined on this closed interval, this interval. Okay, so that was those 2 theorems. And they used some property about that. They used 2 things. I mean, they used like the Bolzano-Weierstrass theorem, right? And then they used how sequences and continuous functions were tied together. The Bolzano-Weierstrass theorem is using something about that the real numbers are ordered, and like this with sup and inf are, you have the least upper bound property and the greatest lower bound property, right? So, okay, now another thing. So we talked about. So like some of the highlights is like in terms of concepts are sequences and continuity of functions, and then various properties that follow from this. Then another thing is series. So that's another key property, a key concept. So series. So series is where you started with a sequence. So series. So you're starting with, so this here is a sequence. And now you form another sequence, Sn, but here you're summing, and it could start wherever you want to start it. Let's say it starts from 0. You're summing the first, in this case it would be, because you're starting at 0, you're summing the first n plus 1. So AI, so this is A0 plus AN, this is like n plus 1 in this case. But you don't have to start at 0. If you start at 1, it would be the first n numbers. So you're looking at, so a series is really kind of the same thing, but you think about it a little bit different, but it's really the same thing as a sequence, where you're starting with a sequence and then you form a new sequence. And then the key question here is, so key question is the series convergent. Convergent or not. Right, and so that's a key question. And if it is convergent, and you often, the series is often written like this, and so this here will symbolize the series, and if the series is convergent, it will also symbolize the limit. So it has two meanings. Okay? But even if it's not convergent, then it will, well, if it's not convergent, you would just write down and you think about this as a series. Now there are some series that are particular, important, and they can then be used to determine whether or not other series are convergent. So let me just review them. And the most important of all is the geometric series. And the geometric series is the series c to the n equal to 0 to infinity. C is just some fixed number, real number, and you're looking at this. And this is the geometric series, and this is convergent. If the absolute value of C is less than 1 and divergent otherwise, and if it is convergent when C here in absolute value is less than 1, then this sum here is equal to 1 minus. But remember two things. One is that when you actually want to evaluate the sum, it's crucial where you're starting. If I had started at 1, then it's not anymore equal to this, but you have to subtract the first element, right? That was missing. Right? So it's really, for convergence, it doesn't matter where you start, but for the limits, it's key. Right? That's one thing, and the other thing is that when you, again, we talked about this, that when you're given a series, even before there's any question, the first thing, when you have a series, the first thing you look at is, does this AN converge to 0 or not? Right? If AN does not go to 0, well, the series is not going to converge. There's no need to apply any fancy test. Right? And for a series, it's always, the question is always whether it's convergent or not. Okay, so that's a geometric series. And then there are two other series that we talked about. And let me just, that not only talked about, but we also determined whether or not they were convergent, and they were used, then we used them to determine whether other series were convergent. But again, the most important of all of them is the geometric series. That's the one that we use to determine whether power series in general was convergent or not. But there are two others that are worth mentioning. One is the harmonic series. The harmonic series is the series where you're summing 1 over n. So this here is divergent. So let's call this second. And then there is like a closely related, let's call it 2.5. That's called the alternating harmonic series. So the alternating was that it was like the harmonic series, but the sign of it was alternating. And this here is actually convergent. And then, so there's 1, 2, 2.5, and then there's 3, and that's the series, this series here. We looked at this series here, and this here was convergent. The only one where we determined what the sum was actually the geometric series. Okay, so that's like some key series. Then there's, when you have a series, there was one concept that we proved to be quite useful, and that was the concept of absolute convergence of a series. And so you're looking at a series, and absolute convergence was that this sum here was convergent. So this here is absolute convergent if this series, where you just the an replaced by the absolute value, is convergent. Okay, so of course a non-negative for a series of non-negative numbers, it's automatically, if it's convergence, it's automatically absolute convergent. And like we talked about it a little bit, that one of the things about an absolute convergence is that you could kind of reorder the way you're summing things, and it wouldn't matter for the limit. But if it's not absolute convergence, that really matters. Like we talked about it, we didn't really prove anything there, but I think it was kind of clear you could do this. One thing where we used it was that when we look at product of series, then the product of series was convergent if each of them was absolute convergence. And there you saw that we estimated some remainder term, and there was really kind of key that we had absolute convergence. Okay? So anyway, so absolute convergence is an important, it's for a series, it's a stronger property than convergence. So absolute convergence implies convergence. Maybe I should write this as a theorem. So we had a theorem, so absolute convergence. So this implies convergence, but it's not. It's stronger. In general, it's stronger. Okay, and now then we had some tests. And so we had we talked in particular about. There was a few other tests that we talked about, but I didn't. They're not actually going to be on the midterm, and some of them we'll get back to. This one here won't be on the midterm either, the alternating. But we talked about how to prove the convergence, right? And the important, and when we talked about it, then we discovered that this thing here, that there was a stronger statement that if you have alternating and the AN were all non-negative, and these guys goes decreasing down to 0, then actually any alternating sequence like that would be convergent. Anyway, but the test we really talked about was 3 tests. One of them had 2 parts. And then in a minute we'll talk about how we applied them to power series, or which one did it. So we had some tests to determine whether or not the series or not as series is convergent. Okay, so what are the tests? So there are the comparison tests. Let me just first write down the test. So the comparison test, and there was 2 versions, version A and version B. Then there was the ratio test. And then there was the root test. The ratio test and the root test, they are both offsprings of the geometric series, right? In both of these, you got, let's just talk about these first. The ratio test was when you're looking at this ratio of an divided by an plus 1 over an. So you are implicitly assuming that the an does not vanish, not 0. Right? So you can form this ratio. And then if this limit here, as n goes to infinity, if this limit here is less than 1, then the ratio tests say that the series was convergent. If the ratio was bigger than 1, then this ordinary element an would not even go to 0, right? So this here is, so that in this case here, maybe I'll write it over here. So for the ratio test, you assume that the none of the an was 0. And you're looking at an plus 1 over an. And if this limit here, let's call this limit, let's assume that the limit exists. Of course, it may not exist, right? But if the limit existed, so if c here is less than 1, right, it's always non-negative, because these are non-negative numbers. If c is less than 1, then the series is convergent. If this c here is strictly bigger than 1, this implies that the series is divergent. And if the c was equal to 1, then it's unclear. And so unclear, which means that further tests are needed. And so now, so that's the ratio test. And the root test was similar. The root test were, so you're looking at the an, you take the, so this is the root test. And again, this is tested by comparing it to the geometric series. So the root test. So you take the an, take the nth root of this, and you're looking at the limit here. We actually looked at the lim sup. I'll write in the lim sup. The reason why I want the lim sup is that I want to make sure that it's later on, I want to apply it more generally. Okay? So I have, so if the lim sup here was less than 1, let's call it lim sup, let's call it c. If c here is less than 1, then series is convergent. true. If the C is bigger than 1, the series is divergent. It fails the most basic test, divergent. And again, 3, if C is equal to 1, then it's unclear whether the test are needed. Okay, that was those 2 tests. The comparison test, let's get back to that. The comparison test had 2 parts. That you had, suppose you had AN and BN. The first part is this statement that if you have 2 series, one based on the AN, another series based on the BN, if you have this, if BN, so this here, if this series here is converted, then it implies that those is converted. Right? And this is sometimes used both exactly like this, and it's also sometimes used where you know that this one here is divergent, and so you conclude that this one is divergent. The other part of the comparison test was if you had the limit here, if this limit here exists and it was something L, then actually it say that, let's say L here is not equal to 0, then if one of them is convergent, the other one is also convergent. So if AN or BN, so BN is convergent, then it implies that AN is convergent. And vice versa, is actually equivalent. This is convergent, even on this is convergent. So those were the 3 tests that we really went through. There was a few other tests, like again this alternating series test that sort of proved, but it's not going to be on midterms, and we will return to this later. Yeah.
Are there like patterns of like when we should apply which tests?
Yeah. No. And I want to get to this. I want to get to this in just a second. Let me just say a couple of words first, and then let me jump to some of the examples of problems, and then I'll come back and I'll review a little bit more. So, but let's just talk about power series. Maybe let me just think. And whether just now when you were asking the question, no, let's just review the power series. So a power series was a series, but it was something that also defined a function, right? And so you take, so you have so power series. So you have a sequence AN. And then you think for each x, but x is being fixed, you form a series, and this is the series that you form. And so for each x, you can ask, is this series convergent or not? Right? This here is called a power series, and the key point for a power series is again, of course, whether or not this is convergent. And this gives rise to the radius of convergence. And so the radius of convergence was that we looked at lim sub of the nth root of AN, like that, right? And we looked at when this thing here, if this thing here is, right, so we defined this thing here, and so we look at this thing here, and then we define the radius of convergence, this is R, and the R is 1 over this loop soup. But there was an understanding in this. The understanding is that if this number here, this number of potential could be infinite, right? If it was infinite, it meant that this thing here was 0, right? If this one here is infinity, if this here is 0, then this here would be infinity. Okay, so that's like a convention in this particular case, right? I mean, usually we don't want to divide by 0 and that kind of stuff, but this is a convention in this particular case. And so using this radius of convergence, we saw that if you take a power series, if you have any power series like this, there you have 0. Any power series like this, it's going to be, if this here is R, and again, R could be 0 or it could be infinity, right? But if this is R, sorry, I should write this in minus, then for x in between, for x, not including the endpoints, but in between, the series is convergent, right? The power series is convergent, and outside here is divergent. Outside is divergent, here it's convergent. And at those 2 points here, I'm clear. Further tests are needed. Right? So this is always this picture. So this comes back to your question about which test. I mean, of course you can use any test you want. But when like if you're looking at a series, you can use whatever test you want. But if it was a power series, you already know that there's some interval around 0 where it's convergent, and then there's a question about the endpoints, right? And so, okay, so now let's look at some examples of this. And suppose you look at, and so it's usually not too hard to use either the root to use either this here was based on the root test, so either using the root test or the ratio test for power. But you can take advantage of it. Sometimes it's just slightly easier. So let's look at 2 examples here. So suppose that you ask to find the radius of convergence. Convergence for the power series. And then let's say that this is n to the 5th power xn. So suppose that this is the power series you're given, and you want to find the radius of convergence. Right? You can either just plug it into this test, right? Or you can just say, okay, we just apply it. We know that it's some interval, and I just want to see for which x does this here converge. So if I looked in this case, you might find it slightly easier to do the root test. So if you're looking at the n+1 element in this series, the n element would be this to the 5th power. Think about x as being fixed, right? And you're asking for which, and then you want to, for a given x, you want to determine whether this series here is convergent, right? So if you were using the root test, you would look at this one here. And you might find, in this case, slightly easier to use the root test. So if you're looking at this thing here is now n+1 to the 5th power times x to the n+1 divided by n to the 5th power times x to the n, right? That's that ratio. And so, of course, you can write this in here this is like n plus 1 multiplied by itself 5 times, divided by n multiplied by itself 5 times. And then this thing here you can write as x to the n times x over x to the n. So you see this thing here you can then think about as n plus 1 over n to the 5th power and times x, right? And I can write this thing here in the usual way. If you want, you can write it as 1 plus 1 over n. I'm dividing by n in both numerator and denominator, so you can write it like this, to the 5th power times x. And so now, the root test, it's asking whether this, the absolute value of this root test would be then asking if the limit here, xn plus 1 over, an plus 1 over an, if this here has a limit, and then it's asking you if that limit is less than 1, if it has a limit and the limit is less than 1, then the series is convergent and it's divergent if it's bigger than 1. But in this case, this thing here, this ratio here is 1 plus 1 over n to the 5th power times x. This is all non-negative, so the absolute value just go in over here. The algebraic property of the limits say that this one here goes to 0, and so raised to the 5th power still goes to 0, right? It's multiplied a bunch of sequences 5 times together, that goes to 1. So this here goes to 1, and so even raised to 5th power still goes to 1. So this here goes to the norm of x, right? And so the ratio test would be that if x here, so ratio test gives you is that if this norm here is less than 1, then the series is convergent. If the norm here is bigger than 1, the ratio is divergent. And it's unclear if the norm is equal to 1. So in other words, you see that the ratio test here gives you directly that the radius of convergence is 1. Right? So, and of course you could apply the root test, right? The root test is great on this here. It's a little bit more, I mean, you have to do a little bit more argument. It's not very hard. But it actually, in this case, the root ratio test would be easier it would be less to argue than in the root test. Let's do one more example of this. So maybe I'll just switch a little bit to, and then I'll come back and review some more stuff. I'll just talk about a few of the problems that I added to the end of my review notes. Again, I'll post this with these problems. And obviously they are, I mean, it's not exactly the problems on the midterm, but it's certainly better. Okay. Also, another thing I want to say is that the homework is graded up to and including 4. So I wasn't actually aware of over the weekend. It was supposed to be handed back within latest a week of when you handed it in, and I just discovered it over the weekend that it was some of them were late. So, but it's fixed. I'm not the grader. There's 2 UAs that are grading and a grader. But it's all fixed now. So the first 4 are you can review those also for the lecture. Okay, so the other series, or power series I want to look at is that, so again, what is the radius of convection? The thing about power series, the nice thing about power series is that, you know, power series also test about series, right? So it's like, you know, so what is the radius of convergence? 4. And now the series is a slightly different series. It's this series here. So this series. Okay, and so now let me again, I mean, you could apply the root test. The root test is the one that sort of just give you an answer. It always gives you an answer, but you know, you may have to work harder to find the nth root. So, and sometimes it's just easier to use the ratio test. So let's use the ratio test again. So an here is n to the 5th power x to the n over n factorial. So if you're looking at an plus 1 over an, maybe I should maybe a little bit right over here. So if I'm looking at an plus 1 over an, so then I have n plus 1 to the 5th power times x to the power n plus 1 over n plus 1 factorial. That is an plus 1. And then I have to divide by this, but when I divide by a fraction, it's like multiplying by the inverse of this, so like this in here, n power x to the n power, like that. And so again, I can write this in here as, so if I just do like I did before, I would have that n plus 1 over n to the 5th power. That's when I take this one here and that one together. Then I have, when I take those two together, I can get rid of the n here, and I just get an x. And then when I look at the ratio of these two, this one here, n plus 1 factorial, you can think about that as n plus 1, and then times n factorial. Right? So this n factorial cancel out with that, and you're left with n plus 1. So this is what you get. And this one here, just dividing it as we did before, dividing this fraction by 1 over n in both numerator and denominator, getting this thing here to the power 5 times x n plus 1. And now you see that if, and this here, I guess it should have been absolute value of psi, so it's absolute value on this. Like that. This one here converts to 1. This one is just x, so this converts to x. And then this here goes to infinity, so the ratio here goes to 0. Right? I'm using the algebraic property of limits, so this is converted to 0. And so you see that it does have a limit, so the ratio test applies, because that limit is 0 for all x. It's going to be converted for all x. So the radius of convergence in this case and of course, on the midterm, don't just say that the radius of convergence is infinite. Explain this in here, and the more detailed, the better, right? Because even if there's some typos, you should definitely get. I mean, I'm not going in midterm either, but you definitely should get parts of it. Yeah.
So to get R, is it always like you divide by the lim sup? Because like, is the thing on the bottom board the lim sup or just the lim?
Yeah. So when you take just a complete general series, then then the radius of convergence is by definition this. This is related to, you asked this question a couple of times ago, that because we started with the ratio test. We did that before we did the root test. And you were noting that in the ratio test, you're always comparing an element to the previous one, right? And so, but in general, right, the series can be convergent even though the next element is slightly larger than the previous. If that keep happening, it's not convergent. But it could happen a few times and then it go really down, right? And that's fine, right? And so that's why, like the root test, right, gives you this general result about that it's always, right? It always works. It doesn't assume that the ANs are not zero, etc. Right? For any particular, and it really should be in super, right? And then it's like defined. It's also, it's a number that's always defined. And again, the way it's stated here, the way the proof goes is it's not comparing to consecutive ANs. In any particular example, the root test may not be the easiest way to argue. Often, if you can, for a power series, almost always, I would say, in a power series, it's almost always easier to use the ratio test. But it requires that the power series has some nice property for this to apply. Okay. Yeah.
So the reason you know that R is infinity for that example was because you know it's convergent for all x, not because.
So in this example here, this here is infinity, which means that this thing here would be 0. Yeah.
But you know it's infinity.
But I didn't actually calculate. You see, I didn't calculate the n booth in this example.
Okay.
But if I had calculated, I would actually, and it's not very hard to calculate, but it needs some small tricks. And so, and we haven't talked about it. So that's why I did it like that. Let me talk about a few other things, and then, so again, I didn't necessarily, I don't think I can probably review all what I had in my review notes, but let me just talk about a few of the problems that I had. But again, so the things let me just quickly mention the things I may or may not get to that I have in my review notes. So I had also property, what is leaf soup, what is leaf inch, and so you definitely review that also. Talk about the radius convergence. Well, maybe this is all, and then talk a little bit about the power series for the exponential functions. But again, all the stuff we did on the power series for the exponential functions, at this point we have established it. This is like, it's more like, there won't be anything particular about, the exponential function itself could be on the midterm, but it's not like you would have to prove the properties of the exponential function. This property, that it has a property that the exponential function of x plus y is like the point of that kind of stuff. It's not on the midterm, okay? So it's not part of this review. The other thing that I probably won't get to, because in a minute I'll just turn to these other problems, is that metric spaces, definitely review metric spaces. It was in the last lecture. So, there's a bunch of, there's 3 properties for a metric space. The distance should be non-negative, it should be symmetric, and the distance between 2 points should be 0, if and only if those points are the same. And then the crucial property in the metric space, then that's like the powerful property, is the triangling property. Okay? And so there was a few examples, and review those examples. They are in my review notes. Like the most important example, I would say, is the French rail metric is kind of, crazy metric. That's not one of the important ones. So I just, in review notes, that's just the most important ones. And then there's this with what does it mean to be convergent in a metric space and what does it mean to be a Cauchy sequence. And so now let's get to a couple of the other problems that I suggested that you look at. And so here are two other problems. And again, I won't get to, there's also problems about metric spaces, and you should definitely look at it, but I don't have the time now, even though it's relevant for the midterm. I just have to pick some. All of the problems that I have 4 problems here, all of these are relevant for the midterms. Okay, so now, suppose you take a sequence. So I have a sequence here, xn. And so often a sequence is defined recursively. So recursively defined sequences. So what does it mean? It means that typically you have the first one is defined to be whatever. And then the next one is defined from the previous one. And so the one I was suggesting looking at here is that you said this here, the first one, right, and then actually and then the next one, let me just do this one here. It's actually simpler than what I have in my notes, but maybe that one. But I just want to, so the next one is defined to be xn over n. Okay. And so then, right, so now the question would be for what A does this have a limit, this sequence have a limit. And so you see that in this case, we only have 4 minutes left, so I want to say a few, but this is also, I just wanted you to review what it means like for a sequence to be defined recursively. Okay? And so you see that in this case, right, you have that this thing here, it is going down, it's actually going down, it even could go down by a fraction, but now it's like, if you're looking at this thing here, if you're looking at xn, this here is definitely going to converge, whatever you start with. So I claim that you will always get that xn here converges to 0. And it's just, you see that when you have something recursively, it's often can pay to just write out the first few terms. So you have xn a, x2 is equal to a over, right, a is also a, right, because it's the previous one. x3 is now a over 2, x4 is then a over 2 divided by 3, so this is a over 6, right, and so on, right. And so if you continue like this, you will see that that it's like a divided by some larger and larger number, right? But you have to, of course, write it nicely out as a proof, right? But this is proving that. But again, this here, if you just did what I did, that would not be enough to get full credit, right? So definitely write out. The other thing, in the last minute here, the other thing here from my example here, suppose you take a series like this, and suppose that an here is less than 1 over n squared, and then the question could be, is the series, suppose you knew this, but that's all you know, is the series convergent or divergent, right? And then I say, in the notes here, I mean in the review here, right, that if either you should prove that for all such series it's convergent, or if that's not the case, you should give an example of a series with this property that is divergent. Right? Because obviously, if all the AN was 0, it would be convergent, right? But it still could be another series with ANs that have that property that was divergent. Right? But in this case, it is going to be convergent. And why is it convergent? Because this series here is convergent, right? We've already seen, and so this here would be like the simple comparison test, like the first comparison test. Okay, so right, so these are just like examples of things you should be reviewing. Right, they are this, like these things here, the two things to the end. They're like this one here. Like this is super fast. So don't expect it to be quite as fast on the midterm. Right? But it just gives you an idea of what you should be doing.